turn on recording now so that we can always go back here and look at this thing. And I have them on my desktop so I can get to it a little easier. It's entitled PH750 Lab Session 4, and it's a Word document. And it's going to refer to a bunch of other stuff that we're going to be working with as well. Okay. Now, I'm gonna step off of that for a second so that, how are we doing now? Most people back already, or am I still missing some people? I think we're pretty much back? Okay. All right, through the magic of...
Someone who's watching from home said the screen was in and out the entire time.
Oh, I think during the lecture, I noticed it was kind of blinking a bit and stuff like that. I didn't want to, I'm not sure why that was going on, whether it was a connection problem. I think the sound was good, but I think the screen was flashing every once in a while. I didn't want to interrupt her while she was lecturing and stuff like that because, I didn't know that it was something we could fix easily here anyway. Because I think maybe it was a connection problem or something. Maybe it was something with Google Hangouts. Yeah, I noticed that. We're on a different system now. We're on GoToMeeting, so I don't think it's occurring now. Okay, I think we should be okay. All right. One of the things I wanted to talk about first, before we really got into this, was the idea of where this idea of normal distribution comes from. I'm gonna make a histogram, and let's say that we have a histogram. That's a pretty ugly line there. Let's say we have a histogram where we're going to take 20 people and we're going to measure their heights. Okay, and I'm going to break up the heights into less than 50 inches. Whoops, less than 50 inches. 50 to 55, 55 to 60, 60 to 65, 65 to 70, and 70 to 75, something like that. Okay, well, let's say 5 of those people are in the range of 65 to 70. Okay, so I'm going to make a bar here. I'm going to draw a histogram and make a bar of 5 people high, right, for that common outcome. Okay, so let's say 60 to 65 inches. Maybe aren't so many, maybe it's 4 people. And less than 60 inches, 55 to 60 inches, maybe not many at all, maybe 2 people, right? And less than 60 inches, let's say maybe there's 1 person. So how many people have we accounted for here? We've got 5, we've got 12 people. Well, now there's going to be some people that are taller than that. So let's say 70 to 75 inches. How tall is that? That's 60 is 5, 7. That's okay. Maybe there's 4 people that are in that range. Maybe 75 to 80. There's 3 people. And I think that's 8 people. That's 7 people. So I think we got 1 more left. So maybe they're just a little bit taller. When I draw a histogram of a naturally occurring normal distribution, height may not be an exactly normal distribution, but it's kind of normal, right? It's kind of one of these things where we would expect most of the, I'm getting an echo here from, is that one of the speakers? Okay, you know what I'm going to do? I'm going to mute everybody. I'll make sure I mute everybody here. Okay, mute all. Okay, got everybody muted, and I think I got the sound turned down there. Okay, so at any rate, we would expect, like, this is kind of a normal distribution. We would expect most people to be an average height and fewer people to be below average and above average. And the further away you get from the average height, less and less people. We wouldn't expect very many people that are 4 foot tall. We wouldn't expect very many people that are 7.5 foot tall, right? We'd expect most people to be in that mid-range between, say, 5 and 6 foot tall, right? So in these kinds of normal distributions, most of the population, most of the cases are going to be in the middle. And we're going to get a diminishing frequency as we go out further and further. Now, it's pretty easy to see that in this distribution, it's kind of herky-jerky. It really doesn't look like much of a continuous function. But if you can imagine, if I did this for 1 million people, and instead of like 60, 65 inches, each division might be 60 to 60.1. 60.1 to 60.2. What am I doing wrong here?
Somebody has it on in the room and echoing.
Yeah, somebody's speaker is on over here on one of these computers. Any idea which? Well, you know what you can do? Just go down and just like mute it or turn the sound down on all the computers, and that should do it. You know, right, there's a little button on the lower right-hand side of the bottom of the screen. You should find the little speaker symbol, and you can turn that down. So at any rate, I don't hear it that much. So I think I'll be able to concentrate. So at any rate, what's going to happen now is instead of having these wide bars, these bars are going to get narrower and narrower, almost to the point where it's a big enough population. They're almost going to be like lines, a series of lines that occur here, right? And the function that we're seeing is here. It really is one on, right? Yeah. The function that's occurring here is going to start to look like a curve rather than a series of boxes. That's going to be our normal distribution. One of the interesting things here is that there's a relationship between the mean for all of these people that are in here, this population, and the standard deviation. Notice I'm using the symbol mu for mean and sigma for standard deviation because I'm talking about a population, not a sample of people, but the entire population of people, maybe the entire population of the United States. So more and more, as we get more and more people, more and more cases represented, this thing will form a bell-shaped curve. This doesn't look like much of a bell-shaped curve. Be more like something like this, more like this, right? It's going to form a bell-shaped curve. Now, sometimes you're going to have a distribution that's very wide, right? And that bell-shaped curve, let me get a fresh piece of paper here. And that bell-shaped curve is going to look something like, right? And the mean here is mu, and the standard deviation here is sigma. Let's say mu could be 100, and sigma could be 20. In other cases, you might get a distribution that has the same mean, but there's a much lower amount of variability in the distribution. So that even though the mean is the same, the spread, or the way these things are spread out, might only be, standard deviation might only be 5. These are both normal distribution. They have the same mathematical properties. The only difference is where the mean might be and where the standard deviation might be. There's a really nasty looking formula, believe it or not, based on the stuff that we did with standard deviation. There is a really nasty looking formula. I'll show it to you over here. This formula represents that curve, okay, where x is the position, like x might be the weight of a particular individual, 120 pounds, or the height of a person, 65 pounds, or something like that. And if you wanted to know what the height of that point is, where that line is, you know, off the above the axis, you would put in here 2 pi times the standard deviation squared times e, which is the natural logarithm function, is 2.7 something, to the minus x minus mu squared over 2 times the standard deviation. Obviously, it's not going to be very easy for us to easily calculate that position on that line using this formula. However, we have tables and we have functions in Excel that'll do that for us automatically. So we're never going to look at this formula again. From now on, we're only going to be considering what we know about the standard deviation and the mean and the distribution called the normal distribution, based on what the mathematics that have already been derived for us. And the first thing that we're going to learn about that is that there's a very interesting, simple relationship between the mean and the standard deviation. And one of the ways it's represented is by this thing called the empirical rule. A lot of people just call it the 99, 95, 68% rule. Okay? In fact, if you Google that, you'll come up with this drawing here. What this drawing is telling me is that in any normal distribution, now remember I told you height was pretty normal, but not perfectly normal. We know weight is not perfectly normal because there are more overweight people than underweight people, most likely. But it's not perfectly normal, but it's, a lot of these distributions are close, and occasionally maybe we get really lucky and get something that's really close to normal. But our assumption that we're going to be using in a lot of cases is that most of the statistics, most of the populations that we're going to be looking at, variables we're going to be looking at as we go forward this semester, we're going to be looking at normal distributions. Later on, as you move on, or if you move on to other advanced topics in statistics, you may be looking at, well, how do I deal with populations that are not normal? And you want to know something, even this semester, we're going to learn that there's a certain way we can apply these rules very effectively, even when a population or is not normal. Okay, we're going to see how certain tricks we're going to be able to use are going to help us there. So what does this 95% rule tell us? That's this 90, 97, 95, and so on and so forth. It tells us that 68% of the population occurs between one standard deviation below the mean and one standard deviation above the mean. So if I told you that the mean weight for a normally distributed population was 150 pounds and the standard deviation was 10 pounds, that would tell you that 68% of the people in that population weigh between 140 and 160, right? That's a pretty useful little thing, right? That also tells you that 95% of the population lies between two standard deviations below the mean and two standard deviations above the mean. Well, what's two standard deviations? If the standard deviation is 10, well, it's 20. So 20 below the mean would be 130, 20 above the mean would be 170. That's 95% of the population. You can actually start to do some tricks now. If I told you if I asked you what percentage in this population, what percentage of the population weighed below 130 pounds? Well, gee, I just told you 95% is between 130 and 170, right? So that means 5% is outside of those. Oh, but look, there's two sides. There's above, there's a tail left above, and there's a tail left below. So that means 2.5% of the people weigh less than 130, and 2.5% of the people weigh more than 170, right? And you can even really finagle this even further as you look, because a normal distribution, one of the other properties of a normal distribution is that they're symmetrical. So if I look at again in this distribution, if I look at the people that weigh below 150 pounds, but above 140 pounds, between 140 and 150 pounds, right? Well, that's half of the area that I was looking at before. That was 68%. So that represents 34% of the people, right? This area in here represents 34% of the people in this population. Okay. So we're going to use this to help us understand this distribution. So let's go to, here's our Word document. And let's start with our problem. Assume the heights of adult Caucasian men have a mean of 68 inches and a standard deviation of 4 inches. Find the probability that a randomly chosen individual from this population has a height greater than 68 inches. What's the mean? 68 inches, right? What's the probability that a man in this population has a height greater than 68 inches? 50%, right? Exactly. Because half of the people mean. That's what mean means. Half of them are below, half of them are above. How about between 64 and 72 inches? How many standard deviations below is 64? One standard deviation. How many standard deviations above is 72? One. And what percentage was between those? 68%, right? Okay. Less than 60 inches. Okay, well, less than 60 inches now is going to be 68 inches minus 60 is 8. That's 2 standard deviations, right? So 2 standard deviations below the mean, that means 95% of the population is between here and here. What percentage is left below the mean? Below 2 standard deviations? 2.5%, right? 95% is between 2 standard deviations below and 2 standard deviations above. So in this case, 2 standard deviations below is, how much was it? It was 68 minus 8, which is 60. The percentage below 2 standard deviations below the means is going to be 2.5%, right? Because 95% is between two standard deviations below, 60, and 2 standard deviations above, which would be 76. So that would leave 2.5% below and 2.5% above. And if I had asked you what percentage of the population is more than 68 and 8, is 76 more than 76 inches tall, it would also be 2.5%. Okay, so I'm really rushing through this a little quickly because we have a limited amount of time. We want to get through all of it, but you can always go back and take another look at this later on, right? Okay, we are recording it, yes. Assume that the heights of adult Caucasian women have a mean of 63 inches and a standard deviation of 3 inches. What percentage of women in this population have a height greater than 63 inches? 50%, again, right? Because the mean, that's the mean. Greater than 66 inches, right? So what would 66 inches be here? How many standard deviations above the mean would 66 inches be? 1 standard deviation, right? So that means that you've got everything up to the mean represents 50%. Plus you got another 34% here, right? So 50 and 34 is 84, right? What does that leave to be above 1 standard deviation above the mean, right? That means 16% is the probability that you would have a woman from that population. Notice how I'm using probability and population, and percentage of the population the same way here, right? If this curve represents the distribution of everybody in this population, well, then the areas of the curve represent the probability that you would pick somebody out that's in that area, right? So if you're looking at half of the area of the curve, if you randomly pick someone out, the probability of them being in that area is going to be 50%, because that represents 50% of the people. Okay, less than 60 inches, 63 inches, right? Is the mean. 60 inches is 1 standard deviation below, which would be below this 34%. So how much is left down here? Again, 16%, right? Well, the mean, up to the mean, everything up to the mean represents 50%, right? So if I'm looking at what's the probability of a woman being less than 1 standard deviation below the mean, right? 34% of the women are between here and 50%. So that means that 50% minus 34% is what's left for them to be below 1 standard deviation below. Okay. The gestation time for humans has a mean of 266 days and a standard deviation of 25 days. What percent of pregnancies would you expect to be greater than 291 days? I'm gonna sketch this one. Okay, let me see if I can't do this. Okay, now this is why we were talking about sometimes it really helps to sketch this stuff. Okay, and I'm gonna get a fresh page here. Okay, and I'm gonna sketch this. Oops. Okay. Okay, what did I say the mean was here? The mean is 266. I'm gonna say mean is equal to 266. And what's the standard deviation? 25. Okay, so let's see what the problem asks us for. Whoops, I guess they won't let me grab that. Problem asks us for greater than 291 days. What's the probability that you would pick out someone with a gestation period greater than 291 days? Okay, so the mean is 266. So 1 standard deviation above the mean would be 266 plus 25, which is 291, right? That's 1 standard deviation above the mean. And what are we looking for here? We're looking for, I don't know why it won't let me grab that. We're looking for greater than 291. So we know that 291 represents 1 standard deviation above the mean. So we know that 1 standard deviation above the mean and 1 standard deviation below the mean, what's this area in here? 68%, right? So that would represent, this represents 34%. This represents 34%. So I know that everything from here to the right is 50% because it's symmetrical. So how much does that leave for this? That's 16%, right? Another way you could look at it is everything to the left of this is 50%, right? This is all 50% because it's to the left of the mean. And you have 34% between the mean and the 291. So you've got 84% represented up to this point. So again, that gives you the same 16%. Okay? All right, we're rushing through this a little bit, but it's pretty straightforward, right? Okay, less than 241 days. Okay, let's take a look at less. I'm going to redraw this because I made such a mess of it. Okay. Mean standard deviation was 25. What was the mean again? What was that? 263?
266.
266. Okay, good. 266. And we know that 291 represent one standard deviation, right? So that was 16% in there. Okay, and now we're asking what percentage of this population is less than 241 days? 241 looks like it's one standard deviation below. Right? So what percentage is less than 241? Right? 16% again, right? It's obvious, right? Because we know that one standard deviation would make this 34%, this 34%, this 16. So the next question, next logical question might be less than 241 days or greater than 291. Less than 241 days is how much? And more than 291 is 16. So right, we just add those together, and 32% of the population represents women that had gestation period less than 241 days or more than 291. If I had asked you the what percentage of women had a pregnancy that lasted between 241 and 291, it would have been the 68% between those two. Good. Okay, good. We're getting a handle on this, I think. Okay, so let's make this a little bit more complicated now. Okay, let's see. Now we're going to get into using some functions in Excel in just a second. Okay, now assume the heights of adult women. Let me see if this is going to come 2 inches. But what percentage would you expect to have mean height less than 63? Standard deviation. Okay, good. This one's going to work out good. Assume that the heights of adult U.S. women have mean of 63 inches and a standard deviation of 2 inches. What percentage of women would you expect to have a mean height less than 63 inches? Easy question. 50% again, right? Because it's less than the mean. Okay, less than 62 inches. We got a problem now, right? Let's see what that problem is. Okay, let me get a fresh page here. Okay, so the mean was 63 inches, and the standard deviation was 2 inches, right? 63 inches, below 63 inches, no problem. We know that's the mean, so half of the women are going to be below the mean. That's 50%. Well, now let's take a look at 62 inches. 62 inches is not one standard deviation below the mean. How many standard deviations below the mean is 62 inches? It's half of a standard deviation. Right? Standard deviation is 2. It's only 1 below the mean. It's half of a standard deviation. So now we have to figure out, what does this area represent? What is that area? Well, we could go get that formula, e to the squared pi and e whatever. We could use that formula, or we could use one of two other ways of solving this. One way is to go to Excel and use Excel to solve this problem. Okay, and if we go to Excel, there's a function in Excel. Actually, I'm going to open something else here. Open recent. Okay. On Blackboard, you will find an Excel sheet that's saved, and it has listed at least 4 functions that you can use in Excel. There are many more that you can use in Excel to figure out areas in a normal distribution. The one I'm going to use, the way I've laid them out here, is that if you know what the mean, mu, sigma is, then you can find the area to the left of that point. So we know what mu, x mu, and sigma are, right? We know the value we're interested in, which is x. We know what mu is, and we know what sigma is. True, we're going to get to in a second. So I'm going to use that function right now. Equals norm. Now you can put norm dot dist or just norm dist. It'll take either one. As soon as I put the parentheses in here, the open parentheses, it helps me out. I don't know if you can see it up there very well. If you have Excel open on your desktop, you might be able to see it a bit better. Under there it says x, comma, mean, comma, standard deviation, comma, and cumulative. Okay? So I'm going to put in there what I know. The value I'm interested in is 62. What percentage of women less than 62 inches? Standard deviation. What was the standard deviation? It was 2. And the next thing it asks me for is cumulative. Now I get to write in either true or false. I don't think it'll take T or F. I think you actually write it out. Right? I got to type in true or false. If I type in true, it means it's cumulative. It'll give you the area from 62 to the left, all the way to the left. So I'm going to type in true. Okay? And not enough arguments. What did I leave out? Standard deviation, x, oh, I'm sorry, I left out the mean, comma 63. Yeah, there you go, comma, I got too many commas in there now. Okay, so now it should work. 62, x, 63 the mean, 2 the standard deviation, and true. And it comes out to about 31%. So what does that mean? That means Excel has just told us that the area to the left of 62 for this particular distribution is 30.8%, or 0.308 if we're going to put it down as a probability. Yes. Do it again? Okay. Okay, so now I'm interested in knowing what the area to the left of the value 62 is. What that area is, what the probability that a woman would fall into have a height of less than 62 inches. I can't use the empirical formula because it's not exactly 1, 2, or 3 standard deviations. So I'm going to use Excel to give me that area. And Excel has functions in it that I can use. And those functions include, the one I'm most interested in right now is called norm dist. Okay, I'm going to make that red so you can see it. I'm interested in that one. And I'm going to solve that right now. I'm going to make this even bigger. Okay, I'll do it over here. Equals norm dist, parentheses, and then it comes up and it gives me a hint. It says, now the following things are what you need to give me. You need to give me what x is, the value you're interested in, which is women that are 62 inches or shorter, comma, the mean, which is 63, comma, the standard deviation. It even gets dark when you get to that point. 2, comma, cumulative, which you're always going to write in true in this particular function. If you write in false, it's going to give you the value for the height of a straight line right at that point to the curve. What's the area of a straight line? 0. It doesn't have, only has 2 dimensions. You need 3 dimensions to have area. It's 0. So it's not a useful function for you. You want an area of the normal distribution. So you're always going to put, for this particular function, you're always going to put in true. And I'm going to hit enter, and it comes out 0.308, or about 30.8%. Okay, so and we can use that again. Okay, let's take a look at the next question. Greater than 66 inches. Well, greater than 66 inches. Let me go back to my notebook. Greater than 66 inches is going to be, let's see, this one standard deviation above would be 65. So 66 would be over here. 66 is 1.5 standard deviations. You want to know something I'll bring up right now? A little prematurely, but I'll bring it up right now. 66 is 1.5. It's 3 more than 63. Standard deviation is 2. So it's 1.5 standard deviations above the mean. The number 62 that we were looking at was 1/2 standard deviation below the mean. From now on, I'm going to talk about, when I talk about standard deviations, I'm going to talk about calling anything below the mean minus anything above the mean plus. So if I tell you that something is plus 1.5 standard deviations, I mean 1.5 standard deviation above the mean. If I say it's minus 2.5 standard deviations, it means minus 2.5 below the mean. Okay, that's something called the z-score. The number of standard deviations above or below the mean is the z-score. That's not important right now, but it's a convention that's going to come in handy later on. Okay, so now the question was, what percentage of the population was greater than 66 inches? Okay, so I'm going to try that norm dist again. No, I'm sorry, norm dist again. Okay, equal norm dist. Okay, and what's the number I'm using here? 66, right? Comma 63, the mean hasn't changed. Comma 2, comma true, and I come up with 93.933, about 93%, or 0.933. Okay, is that the answer to this problem? No, it gives us the area to the left, right? So it's 93%, that leaves 7%. So 7% of the population is taller than that number. Okay, so now I'm gonna, let's see, okay. I'm gonna quickly, let's see. I'm gonna try one more of these and then move on to something else. Okay. Percentage school. Okay, let's percentage of elementary school teachers. Elementary school teachers in the United States have a mean salary of $32,000. Obviously, this was a long time ago. I hope. I hope. It may be true, right? I guess when you start out, it could be true. And a standard deviation of $3,000. Find the percentage of teachers that you would expect to have a salary greater than $36,500. Okay, so slightly different numbers, but the presumption here is that this is a normal distribution again. Okay, so I'm going to get a new chart. Now, one of the reasons I'm doing this each time is so I don't get confused about the areas that I'm working with. So the mean is 32,000, a standard deviation of 3,000. So my mean is 32,000, and my standard deviation is 3,000. And I'm interested in, what am I interested in? The percentage of teachers, or the probability of picking a teacher out randomly that has a salary greater than 36,500. So 36, let's see, one standard deviation, just so I know roughly where it's going to be, one standard deviation would be 35,000, right? Two standard deviations above the mean would be 38,000, right? So what was the salary we're looking at? 36,500. So it's going to be somewhere between these two. Right? I'm going to put it right about here. So I'm looking, what area am I looking for? I'm looking for this area here, percentage above that. So I'm going to use my normal distribution to find the area down here. Okay, now I'm going to do it two ways. First thing I'm going to do is with Excel. Okay, equals norm dist parentheses, and let's see, the number I'm interested in was, what was it again? 36,500, right? And the mean was 33,000, 32,000. And the standard deviation was 3,000, and true. Okay, and again, we got the same number there, because there's 1.5 standard deviations, got the same number. Okay, less than 28,000. Okay, less than 28,000 is going to be equal to norm dist, parentheses, 28,000, the mean, 32,000, comma, 3,000, standard deviation, comma, true, close parentheses, and that's about 9%. Okay, so I know that this area, whoops, go back here. This area, if I go to, what was again, 28,000. So let me see, where would that be? This is 32K. This would be 29K. So 28 would be about here. So the area to the left here would be 9%. This area up here was, what percentage was it again? Anybody remember? Was 93 less, it was about 7, I'm going to call it 7%, make things easy on us. If the question had been, what percentage of teachers make between 28,000 and 36,500, it would be what's left in the middle here. In other words, 9 and 16 subtracted from 100, right, or 84%. Or 1 minus 0.9 and minus 0.7. 0.09 and 0.07 if we were talking about probabilities. Okay, so that's kind of the way we would do it. There's another way for that we could have solved that. And the other way we could have solved that is by simply just looking at the percentage below this point and subtracting the percentage below this point and just leaving the area in between. And actually that would have worked out even easier for us, right? Because if I had done that with Excel to find the area between the two, I would have just had to subtract 93% minus 9%, and it would leave us the area in between 84%. Okay, that would probably maybe a little more accurate. Okay, so one of the other things I might do here is I might say to myself, if I was looking for the area below 28,000, I'm going to do something interesting here. I'm going to say to myself, area below 28,000, how many standard deviations below the mean is that? Well, the mean was 32,000 minus 28,000. It's a difference of 4, right? What was the standard deviation? It was 3,000. I think dropping off to 0. How many standard deviations below the mean is the value 28? It's 4 over 3, 4/3 of a standard deviation, or 1.333, right? Make sense? Okay. In other words, it wasn't quite as neat as over here where we were looking at. Now, is that a positive number or a negative number? It's below the mean, right? So I'm going to make it a negative number, right? Now, how many standard deviations below the mean was 36,500, right? Minus 32 is 4.5, right? 4.5 over 3 is 1.5. It's 1.5 standard deviations above the mean, but it's above the mean, so it's plus 1.5. I'm going to pull up a table that we have in the back of our textbooks, right? And that table looks something like this. You know, I've completely ignored the people online. I haven't looked to see if they have any questions. But I'll get to you guys in a second. I haven't completely forgotten about you. Only partially forgotten about you. Hang on a second here. Let me see. Standard normal distribution. Nope, don't want that. Okay. Here we go. There is a table called C tables. Okay. Remember I called Z the number of standard deviations? And these tables usually start with a little chart to tell you what area is indicated here. This particular table is almost identical to the one you have in the back of your open source textbook. And it says that, gee, if you look up the z-score, if you give me the z-score, the number of standard deviations, I'll give you the area that's below to the left of that. And if it's a negative number, use this table. But then if it's a positive number, use this table, because that'll give you the areas from that side of the mean all the way down. Both of them are cumulative, just like the norm dist function is. Okay, let's see if we get the same answer. What did we say it was again for 28,000? It was negative 1.33. Okay, well here's negative 1.3, right? Now the only problem is what about the next decimal place? Well, the way you use this table to find the next decimal place is you find the first 2 digits in this first column, and then you go across columns in order to find the third digit. So negative 1.33, negative 1.30 would be this area. Negative 1.31 would be this area, 2, 3. So the area would be 0.0918. That's the same thing we found using Excel. Now, what about the other area that we were looking at? That was 1.5 plus 1.5. So plus 1.5 is going to be, well, it's 1.50, right? So we don't even have to go across. It's going to be plus 1.50 or 93.32% of the distribution is to the left of 1.5 standard deviations above the mean. Okay, so you can use a table to do these calculations, or you can use Excel to do these calculations. Either way should give you the same answer. Excel is going to be a little bit more accurate because Excel, remember, they have to give you, they can only give you the possibilities that can fit on 2 pages. Excel can calculate an accurate standard area for if you told it that the z-score was 2.3339473, it would calculate a different one than, one digit off or something like that. Okay, so it's a little bit more accurate in Excel. But usually this is good enough for government work. A lot of people use the tables instead. Okay, so let's take a look at the next problem. Yes, of course. I'm sorry. The question was, do we have to know how to do it both ways? No, you don't really have to know it both ways. The only problem is that the presumption is you have both ways available to you, right? Let's say you come in here to take the test and all the computers are not working. Okay. So now you need a table, right? Okay. Or on the other hand, let's say the computers are working, but you can't get onto the internet. So you can use Excel, but you can't go online to find the table, right? So, and not only that, but if you sketch this out, it gives you an opportunity to say, am I looking at the right area? Is the number on, in other words, if I had asked you what percentage of the people, these teachers make more than 36,500, and you had sketched that, you'd say, oh, it's a little area up here. But the answer came out to be 93%. By looking at the sketch, you would know you're wrong, right? So sketching it helps you that way. Doing it both ways, having the table and Excel, will help you out too. What if you reverse the two numbers inadvertently? You put the mean first and the standard deviation second, and you get the wrong percentage. Then when you look at the table, you'll realize you had got it wrong because you didn't get the same answer. So it's nice to be able to do it both ways because you can check yourself that way. And it's always nice to sketch this because it'll help you avoid a lot of silly errors that way. Okay, so let me just check online how see how those guys are doing. You guys still awake out there? I forgot to add the mean. Okay, yeah, thank you. We caught that. Okay, yes. I'm getting corrections. Okay, you guys okay online? Okay, good, excellent. All right, good. Sorry to ignore you for so long. All right, so now, okay. Where shall I go now? Okay, let's see. Okay. Two-tail probability, right-tail probability. This, okay, this I'm just working through this stuff. Okay, body mass index. Questions, okay. Okay, value. Yeah, these kind of like, okay. So now I want to get onto binomial distribution. Okay, here we go. There's binomial distribution. We have a few examples of it here. Okay, I'm going to start off with, rather than those examples, I'm going to start off with a discussion of what it means to start off, to begin with. Binomial means that there's two possibilities.
Can you do number 7 before we move there?
Okay.
Just because it's a little bit different than the other one.
Let me see number 7. Number 7. Okay, assume that the blood pressure reading a mean of 120, a standard deviation of 8. What blood pressure would you expect to exceed the highest 10% of this population? That is different. Okay, so now what is that asking you? Let's sketch that. It's kind of taking a look at this problem from the opposite direction, isn't it? Okay, so now let's see what this looks like. Let's see if I got one of these with a chart on. Okay, so now what do we know about the distribution of blood pressure readings? Mean's 120, standard deviation is 8. Okay, so the mean is 120 and the standard deviation is equal to 8. Okay, mean is equal to 120. 120 down here too. Okay, so the question is, what blood pressure would you have to exceed to be in the highest 10% of this population? Okay, well, I'm just going to draw this anywhere here. I don't know where it would be. But we want to know what blood pressure is represented so that this area is equal to 10%. Right? Okay, so we want to know what that is. What that's our X. We want to know what that is. What blood pressure that has to be. Okay, so now we know the mean and we know the standard deviation. Let me go over to Excel. See if there's any other function there that'll help me with this. Okay. Okay. Norm inverse, right, allows you to put in a percentage, a mean, and sigma, standard deviation, and get what the value that's represented by that percentage is. Okay. So this has, the input has every stuff we know. The percentage is 90. What's the percentage that we want? It's 90%. I gave it away. I'm sorry about that. Right? It's not 10%. It's 90% because we're always working to the left. 90%. And the mean is we know 120, and sigma is equal to what, 8, I guess, or whatever it was. And that'll help us solve for x. So let's give that a try on in Excel. Okay, well, we're in Excel, so we can give it a try right now. So I'll do it right underneath here. Okay, equals norm. And it kind of makes sense to call it norm inverse because you're doing the inverse of what you normally would do. Inverse parentheses, and it's asking me for the probability, which is 0.90, comma, the mean, which was 120, and am I right about that? And the standard deviation, which is 8. Am I doing this right? Yes? Everybody agree with me here? Okay, so what is the value for x? It's 130.25. So we know that x has to be 130.25 in order for this area below it to be equal to 90%. So if you're in the top 10%, you have a blood pressure of 130.25 or higher. How could I do that with the table? Could I do that with the table? Sure, you could do that with the table also. Okay, and the way you could do that with the table is, remember, the areas are inside the table. Let's see if I can't find the table again. The areas are inside the table. Let's see, as I said. Oh, that's not one. Keep opening the wrong one. See table. Say, now the areas are inside the table. So what area represents 90%? Well, I'm going to scroll through this until I find the area that represents 90%. 90%, the closest one to 90% looks like this right here, which is, well, maybe this, maybe that, there, yeah, maybe this one. So about 1 point, I'm going to call it 1.3. It's really 1.29 or something, not 2.8 or 2.9. I'm going to call it 1.3 and call it 90%, call it 1.3. That's 1.3 standard deviations above the mean. In other words, the value, 10% of the population, is 1.3 standard deviations above the mean. If the standard deviation is 8, I could take 8, multiply it by 1.3, and that'll come out to be 8 times 1.3 is going to be 10.25. So that means 10.25 added to 120 is 130.25. I can use it to tell me how many standard deviations above the mean the area to the left being 90% is, and then I could work backwards from there and say, well, in order to be 1.25 standard deviations above the mean, you have to be this much more than the mean is, right? Or you can just use the Excel norm inverse. Okay, so that is a little bit different way of using these tables, to find the same kind of information, but from a different direction. Okay, so now let's go back and take a look at this binomial distribution. So binomial distribution involves 2 possibilities. In other words, remember, we had the coin flip, heads or tails, right? If I flipped 50 heads and 50 coins, I'd expect to get 25 heads, 25 tails. But each time I flip 50 coins, chances are I'm not going to get 25 heads and tails. I may get 24, 22, 31, 19. Overall, the most common outcome will be 25 out of 50. But a little less common will be 24 out of 50, or 26 out of 50, or 27, and so on and so forth. If I'm talking about diabetics, and I told you that 10% of the population is diabetic, if I sampled 100 diabetics, if I randomly select 100 people rather, what percentage of, or how many of them would I expect to be diabetic? 10% of the population. Does that mean I'm not going to occasionally sample 100 people and not get 9 or 11 or maybe even 0 in a very rare instance, right? Well, the binomial distribution helps us figure out what that probability is, okay? And the way we're going to use it, I'm going to give you an example of a binomial distribution and some interesting properties for binomial distribution. This sketch is a sketch of, think pinball. It's a sketch of something called a Galton machine. A guy named Galton developed this. Okay, what happens here is he drops metal balls into the top here. And those metal balls come down and they hit a little bar, right, like a pinball machine. Or, yeah, you guys ever hear pachinko? It's a Japanese kind of pinball game, gambling game. It's going to hit one of these little bars. It could go to the left or to the right. If it's lined up right, 50% of the time it'll go to the left, 50% of the time it'll go to the right. And then when it bounces off there, it bounces down to the next one. 50% of the time it'll go to the left, it'll go to the right. Right? So balls are going to pile up down at the bottom. And where's the most likely outcome? Think heads and tails. Equal number of left and right turns. So the most common outcome is going to be right in the middle. And in order to get all the way over here, it's got to make 1, 2, 3, 4, 5, 6 more left turns than it makes right turns. In order to get over here, it's got to make 6 more right turns than left turns, right? So you would expect less frequency, less times that this is going to occur here. If you go to the New York Hall of Science, which is in Queens, they actually have one of these operating there continuously. Let me move this over here, and this is a little video of it operating. Okay, there you go. Can you see the balls coming down? And they're hitting those bars, and they're randomly going to the left and to the right. And they go all the way down to the bottom. They accumulate down at the bottom. Okay, and this is happening in real life. This is not a rigged machine or anything like that. And sure enough, if you go down to the bottom, it's forming a normal distribution. It's not really a normal distribution. It's a little bit different formula-wise than a normal distribution because it's binomial. Okay, it approximates a normal distribution. It's a little bit different, right? It doesn't really obey the exact laws, but you can see in real life they're actually piling up like pretty much the way you would expect them to. Okay, so binomial distributions we can view kind of when we do many of them as normal, the outcomes being normal distributions if we repeat the sampling over and over and over again. So we want to know what's the probability now of having these various kinds of outcomes for the binomial problems. Okay, and I'm gonna do this verbally for starters. Okay, I'm gonna make this real big, 100%. Good. Okay, so now I'm gonna take the problem with diabetics, and I'm gonna say I want to estimate. I want to know if 10% of the population is diabetic, and I want to randomly sample 10 people in this population, and I want to know what's the likelihood that I will get exactly one person that's diabetic. Or what's the likelihood I'll get exactly 2 people that are diabetic? Well, since I'm taking sample of size, remember we were flipping the coin? And when we flipped the coin, in order to figure out all the different outcomes and what the probabilities were, we built a probability tree. And when we were working with just three coins, right, it got like we were starting to run out of paper there, right, towards the end. Imagine doing this for 10 coins, 10 tries, 10 coins. You know, how many heads, how many tails? We need we need the whole wall here for all the outcomes, the possible outcomes, to figure out the probabilities. You don't have to do it using a probability tree. You can do it using a formula. And the formula looks like this. Okay, here we go. There's a better version of the formula. This is what the formula looks like. The probability of X number of successes, in other words, success being that the person meets the criteria, like they're diabetic. Probability of getting, let's say, 3 diabetics out of 10. I'll call X is going to be 3. Let's say I promise. Let's probably getting exactly 3 diabetics out of 10. Probability getting exactly 3 diabetics out of 3 is equal to n factorial, the number in your sample. That's 10, right? 10 factorial. What's 10 factorial? 10 times 9 times 8, and so on and so forth, over x factorial, that's 3 times 2 times 1, times n minus x factorial, 10 minus 3, 7 factorial, times the probability of success, which was 10%, to the x value, to the third, times 1 minus p, which is 0.7, right? 0.9 rather, to the again to the 10 minus to the 7, again at 10 to 10 minus 3. Okay, so you'd have to work that all out, right? Kind of cumbersome, right? Excel does that for you. This actually will calculate the real binomial probability, but that's kind of cumbersome. So Excel has a function in it called binom dist. Okay, so I'm gonna look that up. Equals. Okay, and this equals binom. Oops, binom. Again, it's dot dist. You don't have to put the dot in if you don't want to. Parentheses, and it comes up with suggestions. I'm sorry, I can't. This one is one of the few things on here I can't really blow up. Binom dist comes up with a suggestion. Inside here now, it's asking you for the number of successes. That's the number of people that have diabetes. I'm going to put 3 in there, comma, the number of trials. I'm going to put 10. Trials is the sample size. Okay, the probability of success, probability any individual has in that population has diabetes is 0.1, and cumulative. Now, true and false here means something. I asked you before, what's the probability of exactly 3 people having diabetes? So I don't want a cumulative. Cumulative is going to give me the probability that 3 people, or 2, or 1, or even none, all added together, all probabilities added together. So I'm going to put in here false. Okay, and I'm going to close the parentheses and hit return. And the probability is less than 6%. Why is it less than 6%? Because we wouldn't expect to get 3 out of 10 very often, right? So I'm going to do something interesting here. I'm going to put in all the outcomes here. What are all the outcomes? It could be 0, and it could be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 out of 10. Okay, and in this column here, I'm going to calculate the probability for exactly that outcome out of 10 possibilities. That's going to be equal to binom dist, parentheses, okay, the number of successes. Well, instead of putting a number in here, I'm just going to click next to that number here. Put that number in there, C2, comma, number of trials. Trials always going to be 10. The probability of success is always going to be 0.1, and false for cumulative. Okay, the chances of having no diabetics when you select 10 people is almost 1/3, 34%. How about 1? Well, I can calculate all these other probabilities just by copying it down, and it'll adjust for me. Let me do it this way. There's all the other possibilities. Okay, so if I add all these possibilities up, what do you think it's going to come out to? Good, 1, right? Because if you look at all the possibilities added together, they're going to come out to be 1. Okay, so now if I ask you, what's the probability of getting exactly 2 people out of 10 that are diabetic? If I randomly sample 10. 0.193, right, exactly, 19% or 0.193. What's the probability of getting 3 people? 0.057. What's the probability of getting less than 4 people? Well, one way for me to do that, what would satisfy that? Less than 4 people. 3, 2, 1, 0. 4 wouldn't satisfy that. If I said it's probability less, right? So what's it going to be? It was equal to the sum of all 3, probability of getting 3, 2, 1, and 0. Oops, I messed that up. Yeah, equals sum. Okay, and it's 98%. Okay, so now one of the tricks I can do here is remember that true or false for cumulative equals binomial dist parentheses. Except this time I'm going to put in let's see, number of successes is 3, comma, trials is 10, comma, 0.1 is the probability for any individual, comma, and this time I'm going to put in true for cumulative. And that's going to be 3 or less, includes 3, but it'll be 3 or less. I get the same answer. Okay. So now you have to be a little careful. You can use that function, but you got to be a little bit careful. For instance, if I wanted to use that function to determine what's the probability of getting more than 4. 2 ways for me to do that. Equals sum more than 4. What does that mean? That means 5, 6, 7, 8, 9, and 10. Right? That's what it comes out, 1/10 of 1%. Right? Now, if I wanted to do it using the cumulative function, it's going to be equal to binomial dist parentheses. Now 5 doesn't. What did I say? More than 5 or 5? I said more than 4. I said right. More than 4. So it included 5. So I want to know everything below. So I'm going to use for more than 5. More than 4. I'm going to put 5 successes. I'm going to put 4 successes, comma, 10 trials. I said, 10 trials, comma, 0.1, comma, true. And that would give me the likelihood that I would get 4, 3, 2, 1, and so on and so forth. So if I wanted to know what's the probability of getting 5 or more, I would just subtract that from 1. Yes. Sure. I put in true to get Q. In other words, if I had asked you, what's the probability of getting 5 or more people that are diabetic, right? 5 or more. Those all satisfy that, right? All of those probabilities. So one way I could do this is I could add them all together, take the sum of all of these. That's what I did there. Sum of all of these right here, right? So the probability of getting 5 or more people that are diabetic is 1/10 of 1%, or 0.16%, okay, or 0.016, whichever way you want to look at it. Another way I could do this is I could say that it's equal to, right? What is it? I could find the probability of 4 or less and subtract it from 1, right? I could take all of these probabilities and subtract it from 1. One way I could do that is to say equals the sum of all these probabilities, right? Subtract it from 1. And what's left is what's in the red, right? That makes sense? The other way I could do it is I could say, okay, equals binomial dist parentheses. And now I'm going to put in, I want to find the probability of 4, 3, 2, 1, and 0 all together. I'm going to put in 4, comma, 10, comma, 0.1, comma, true, because now that'll give me the probability for 4, 3, 2, 1, and 0, and I should get the same answer I got before when I just added those together. And now I can say 1 minus that. I get exactly the same answer. Okay? And you can use this anywhere you have a binomial distribution. And the problem, then it turns into word problems. What's the probability of 3 or more, or between 2 and 5, or so on and so forth? You got to just sit there and kind of figure it out. We kind of we butted heads with the end of the session. But if you got a couple of questions, maybe we can stretch it a little bit. Questions?
Just have one question. Let's say, in this case, we only have 10, but if we had a lot more trials, we would have a lot more data. And we wanted to calculate using Excel the cumulative.
Okay, give me an example. let's say you had 1,000 trials. You sampled 1,000 people, and the probability of HIV in that population is 1.5%, right? Okay, what's the probability that? Okay, the probability. I'll write this out first. Okay, let's say you have your sample size is 1,000, right? And your probability of someone being HIV positive in that population is 0.015, 1.5%. How many people would you expect the most common outcome out of that if you sampled 1,000 people in that population? You'd expect it to be N times P, right? Or 15 people is what you would expect. Okay, now you say to yourself, I want our clinic to be prepared. We're gonna examine 1,000 people a month. I want to be prepared for at least 20, the case where 25 people who are HIV of those 1,000 people might walk in. What's the probability that I would have 25 or fewer people that I would be okay, or say more than 25 people? Well, the probability that you would have 25 people out of 1,000 is going to be binom dist, parentheses, number of successes that you're interested in is 25, comma, probability is going to be the number of sample size is 1,000, comma, number of trials, in other words, is going to be 0.015, comma, and it's going to be true for cumulative. That's going to give you the probability that you get 25 or fewer people, and you'll have the supplies you'll need to treat those people. Okay, and it comes out to 99.4. What's the probability you won't have the supplies? In other words, you'll have 26 or more. It's going to be equal to 1 minus that number. Now, did you notice something I did that was interesting there? I said to myself, I could look at this almost as a normal distribution. Remember those balls falling down and forming a normal distribution? What would be the average number of cases I would expect? 15 cases is the average. The mean is equal to n minus p. And my distribution, my standard deviation, is going to be equal to the square root of n times p times 1 minus p. I don't really have time to explain that much right now, but you'll have to take my word for it. But the square root of the standard deviation of this is going to be equal to what that formula represents. In other words, it's going to be equal to the square root of, what do I have here? 1,000 is n, comma, times 0.015 times 1 minus that, which is 0.985. So standard deviation is going to be 3.84. So we would expect that your normal distribution, your distribution of possible outcomes, would have a mean of 15 and a standard deviation of 3.8. And that would describe all of the possible outcomes for every time you took 1,000 people from that population and counted how many of them were HIV positive. Okay, it's a little confusing, I understand, but this is your first look at it. Okay, after about the fourth or fifth look, it'll make more sense.